Starting with today's lesson, the course is going to head in a more theoretical direction. We started with the concrete, systems of equations. From systems of equations, we developed matrix notation and showed that matrices were quite convenient as far as solving systems of equations. Today's lesson, we're going to start developing mathematical entities called vector spaces. We're going to start with the familiar vectors that you've already dealt with in the plane and in space. Then we're going to extend the vectors beyond things that you can see. After working with vector spaces, we are going to discover that matrices are really elements of some vector spaces. So the matrix that we've been developing can be an element of a vector space. So we will have completed the cycle. And then we're going to show that vector spaces having matrices as elements are remarkably similar to many other vector spaces that may have other elements. Vectors in a plane r squared, whereas it's the real numbers cross the real numbers. X-axis instead of real numbers, the y-axis instead of real numbers, so r squared, are represented geometrically by directed line segments. The length of the segment indicates the vector's magnitude, and the orientation indicates the vector's direction. Let's illustrate a velocity of 30 miles per hour in the direction of north, 30 degrees east. But in order to demonstrate that, we need some scale that we're going to be using so I can get what 35 miles per hour would be like. So I'll create a scale down here that we can go with, and we'll let each centimeter represent 5 miles per hour. So then it would take 7 centimeters to represent 35 miles per hour. So I need some scale. So I need a starting point, and north is generally taken to be up, so I'm just going to draw a dotted line indicating north. And we want to illustrate a velocity of 35 miles per hour in the direction of north, 30 degrees east. So here we would have north, and then 10, 20, 30 degrees east. So that would be the orientation. And remember, if 1 centimeter represented 5 miles per hour, it would take 7 centimeters to represent the 35. So go up to 7. And I'll write on it 35 miles per hour, and I'll show 30 degrees. So we have illustrated a velocity of 35 miles per hour in the direction of north, 30 degrees east. Let's do more geometrically. Here we have vectors u and v. Let's illustrate 2u and u plus v and u minus 0.5v. Well, we have what u is, and we can see that the magnitude of u is going to be about 4.7 centimeters, and I'm just going to try to keep it. So then 2u would be twice that long, so that would be about 9.4. So I'm going to try to just line it up so it's about with u. My orientation seems to be the same. And this would be the vector to u. Same orientation as u, twice as long. Now u plus v, I come same orientation as u, so I'm just going to draw u. Now to add v to it, I put the tail of v at the head of u, and I keep v's orientation, so that's a little over 2. So need to keep v's orientation. You can see that I basically have it here. So this is u plus v. And the actual answer of u plus v will then be a vector from the beginning of u up to the head of v. So this is u plus v. So to find u plus v, I put the tail of v at the head of u, and then the resultant would be the sum. U minus 0.5v. Well, u minus 0.5v is the same as u plus a negative 0.5v. So again, I need to do u. So I keep the orientation the same as it was here. So come down and do u. And I'm going to add now, if v is going this way, the opposite of v is going the other way, and it would be about half as much because it's 0.5v. So notice I'm keeping my orientation the same, except it's going to go backward now because it was negative, and half of v would be just a little over 1. So this would be a negative 0.5v. So here I have u minus 0.5v. Vectors can also be represented by ordered pairs. The vector u, which is equal to ordered pair 1, 2, can be represented by a directed line segment whose initial point is the origin and whose terminal point is 1, 2. So if I start at the origin and go to the point 1, 2 and draw the vector, that would be the vector represented as the ordered pair 1, 2. U is equal to 1, 2, and V is equal to 3, 1. So let's illustrate u, v, 2u, and u plus v on the graph. Now with u, I start at the origin and I go to 1, 2. So here's a graph. And notice we are counting by 2's. So this, if this is 2, this would be 1. So up here is going to be 1, 2. So start at the origin and go up, and that is the vector u. I'm going to run out of space to write, so I'll just show you. That is the vector u, which is the vector 1, 2. V is the vector 3, 1. Here is 3, up here be 1. So up 3, out 3, up 1. And this will be the vector 3, 1. So that's the vector v. We wanted to show 2u. Well, 2u will be the same direction as u, but twice as far. So rather than going 1 and up 2, I'll go 2 and up 4. Same direction, but it will go twice as far. So there is 2u. Notice it's the same direction, but the magnitude would be twice as much. And finally it said do u plus v. Well, we already have u listed. Up to here was u. And v was 3, 1. So I go over 1, 2, 3, up 1. So from u, I added v to it. V vector. Then, so this is u plus v, and u vector plus v vector. The resultant then comes to the origin and goes here would be the u plus v. Let's look at some definitions. That u be written in ordered pair form as u1, u2, and b be written in ordered pair form as v1, v2. Vector addition. U plus v is u1 plus v1, u2 plus v2. Well, you can see that in the last example that it works right out with vector addition. Notice the answer would be 4, 3. If you go back and you simply add the components, 1 plus 3 is 4, 2 plus 1 is 3. So we can tell, at least from our example, that the definition seems to be reasonable. Now, of course, in definitions, you don't prove them. That's just, it's defined to be that way, and that's the way it is. Scalar multiplication. Cu is Cu1, Cu2. So I multiply the scalar by all of the components. It's an example. U is a negative 3, 6. V is 1, 5. So U plus V would be a negative 3 plus 1, 6 plus 5. Negative 3 plus 1 is negative 2. 6 plus 5 is 11. So u plus v would be the vector negative 2, 11. Negative 3 plus 1, 6 plus 5. 2u would be 2 times negative 3, 6, which would be 2 times negative 3, 2 times 6. Two u minus 3v would be 2 times negative 3, 6, minus 3 times 1, 5, which would be a negative 6, 12, plus a negative 3, negative 15. Negative 3 times 1 is negative 3. Negative 3 times 5 is negative 15. Negative 6 minus 3 is negative 9. 12 minus 15 is negative 3. While one loses the geometric interpretation, one can extend the concept of vectors into n space, Rn. If u is equal to u1, u2, u3, un, and v is equal to v1, v2, v3, vn, then u plus v would be u1 plus v1, u2 plus v2, out to un plus vn. Same idea, you just add components. For scalar multiplication, you just multiply the scalar c by all the components. If u is equal to negative 1, 2, 6, and v is 2, 4, negative 5, then 2u plus v would be 2 times negative 1, 2, 6 plus 2, 4, negative 5, which is negative 2, 4, 12 plus 2, 4, negative 5, which is going to be 0, 8, 7. 2 times negative 1 is negative 2, 2 times 2 is 4, 2 times 6 is 12. Then just add the components. A negative 2 plus 2, 4 plus 4, 12 plus a negative 5. Let's look at the properties. Properties of vector addition and scalar multiplication. Let u, v, and w represent vectors in n space, and let c and d be scalars. In other words, c and d are real numbers. The first is the closure property. So this is the closure of addition. U plus v is a vector in n space. So that's called the closure property, closure of addition. The second property is the commutative property of addition. U plus v is equal to v plus u. The third property is the associative property of vector addition. U plus v plus w is u plus v plus w with the parentheses changed. Here I'm grouping u and v. Here I'm grouping v and w. The fourth property is the identity property. U plus the 0 vector is U, and the 0 vector is going to be the vector 0, 0, 0. The fifth is the additive inverse property. U plus the additive inverse of U is 0. So this is the additive inverse property. The sixth, Cu is a vector in Rn. Now this is the closure of scalar multiplication. Closure of scalar multiplication. This is the distributive property of scalar multiplication over vector addition. If I have C times the quantity U plus V, that's the same as Cu plus Cv. So I distribute my C. The eighth property is I distribute the multiplication over scalar addition. So if I have C plus D times vector U, that's the same as Cu plus Du. So I'm multiplying the U times the C and the U times the D. The ninth property is kind of an associative property of scalar multiplication. Here I'm multiplying D by the vector and then multiplying it by C. Here I'm multiplying the two scalars and then multiplying by the vector. And the 10th property, 1 times U is U. So if I multiply scalar 1 by U, I get U. That's the identity property. Now, since these are properties, they can all be proven, and all of them are fairly easy to prove. Proofs of all properties follow the same pattern. Use the definition to write in coordinate form. Use the properties of real numbers to make the desired change. Convert back to vector form. I'm going to prove a couple of them for you just to show you how it works. So let's look at the proof of 2. This is pretty easy. U plus V is equal to V plus U, the commutative property of vector addition. Now step 1 is use a definition to write in coordinate form. So I'll put here, let the vector U be U1, U2 out to U to the n, and V is equal to the vector V1, V2 out to V to the V sub n. So then U plus V would equal to U1, U2, so forth, out to U to the n, plus V1, V2, out to V sub n. Well, by the definition of addition, this is going to be U1 plus V1, U2 plus V2, out to U to the n plus V to the n. But now these components are simply real numbers because we're in n space, r to the n, so it means all the components are real numbers. So since I know that real numbers addition is commutative over the real numbers, I can rewrite this as V1 plus U1, V2 plus U2, Vn plus Un. And now I'm getting in step 2 now. Use the definition, write in coordinate form. I did that. Use the properties of real numbers to make the desired changes. So I changed the order here. Now convert back to vector form. So this is going to be V1, V2, V3 out to Vn plus U1, U2 out to Vn. Now I put V3 and remember I'm leaving them all out so I can put as many as I want to. This would be V plus U, and we proved property 2. Let's do another proof. Let's look at proof of property 7. And you'll probably get a chance to prove most of the rest of them either in homework or on test. We want to prove that C times U plus V is equal to CU plus CV. Let U equal to U1, U2 out to U to the N, and V is equal to V1, V2 out to V to the N. Now C times U plus V is going to be C times, I'm just going ahead and add these now, C times U1 plus V1, U2 plus V2 out to UN plus Vn. That would be the U plus V. Just add the vector U to the vector V by adding components. Well, by scalar multiplication, this is the same as C times U1 plus V1, C times U2 plus V2 out to C times UN plus Vn. Now these are, the components are just real numbers. So within the real number system, multiplication is commutative. I mean, multiplication is distributive over addition. It is commutative, but that was the last proof. Now I'm proving that it is distributive over addition. So this is going to be C U1 plus C V1, C U2 plus C V2 out to C UN plus C Vn, which is the same as the vector C U1, C U2, C UN plus the vector C V1, C V2 out to C Vn, which is the same as C times U1, U2 U to the N plus C times V1, V2, V to the N, which is the same as CU plus CV. And so we proved it. here's a definition that's extremely important to the rest of linear algebra. If vector x is equal to c1v1 plus c2v2 plus c3v3 out to c and vn, then x is a linear combination of the v vectors. So the v vectors are the v1, v2, v3, and so forth. And if x is equal to some constant times those added up, then x is a linear combination of the vectors. Example, write -1, 7, 2, that's vector x, as a linear combination of the v vectors 1, 5, 5, 2, -1, 3, and -3, 2, -4. Well, we must find C1, C2, and C3 such that the x vector -1, 7, 2 is equal to C1 times V1 plus C2 times V2 plus C3 times V3. Or we get that -1, 7, 2 is equal to C1, 5, C1, 5, C1 plus 2, C2, -1, C2, 3, C2 plus a -3, C3, 2, C3, and -4, C3. Where I have -1, 7, 2 is equal to, now I'm going to add the components, so that would be C1 plus 2, C2 minus 3, C3. That's when I added the first components. Add the second components, 5, C1 minus C2 plus 2, C3. And the third components, 5, C1 plus 3, C2 minus 4, C3. Now if I have the two vectors equal, that means their components are equal. So by equating components, I can get that -1 is equal to C1 plus 2, C2 minus 3, C3. I can get that 7 is equal to 5, C1 minus C2 plus 2, C3. Now I can get that 2 is equal to 5, C1 plus 3, C2 minus 4, C3. Well, we're back to solving a system of three equations having three unknowns. I went to derive and I told it to solve. I went to expressions and I typed in solve, parentheses, then I put in the three equations. Now I used x, y, and z in place of c1, c2, and c3. But I said solve, here's equation 1, equation 2, equation 3. Then I had to put the variables x, y, and z, just a standard notation for having derive solve it. And derive gave me that x was 3/2. Well, x stood for c1, so I know that c1 is 3/2. c2 is a negative 13/2. And c3 is a negative 7/2. Well, we were supposed to write one vector as a linear combination of the others. So now with these values of c, I can go back and do that. So I can say that a negative 1, 7, 2 is equal to c1, which would be 3/2 times v1, which is 1, 5, 5, minus c2, which would be a negative 13, well, be plus a negative 13/2, or minus 13/2 times v2, which is 2, negative 1, 3, minus 7/2 times v3, which is negative 3, 2, negative 4. So I've written the x vector as a linear combination of the v vectors.